All right, guys, today we are going to continue with Unit 3, Section 1, which I have the video for Part 1 of Section 1 that went over electron configuration. And we stopped because there was a lot of information in that. And even though that's not a difficult topic, it did take some time to get to how to do electron configuration. So let me get back to that. All right, so if you remember, electron configuration is where we are pretty much mapping out what the electrons would look like, where they would be in an atom. And we said that you had energy levels, you had the different shapes to the orbitals. And if you remember, you had the S shape, which was the spherical ones, and the P-shaped orbitals, which are dumbbell shaped. So at this point, just so you know what the letters were, to refresh your memory, what they stood for. And then you had, of course, energy levels, and we talked about, 1, 2, 3 energy levels. As you move away from the nucleus, the energy gets, increases. And then we said how many electrons can fit in those various energy levels. And you can see that you can have multiple sublevels within energy levels. So I showed you this periodic table and told you probably don't have to memorize this to make this easy. But once you know the periodic table and the layout here, it's not hard at all. Okay, so we did the example for oxygen, and then we went into fluorine, and I did one for phosphorus. Like I said, if you don't remember how to do this, please go back and watch the other video because I don't want to waste too much time on that. Plus, I also have a video here linked that you can go, that's someone else talking, but at least it gives you a different perspective. All right, let's get to what we're going to talk about today. We also talked about noble gas configuration, and this is just kind of a shorthand way to write out as you get along the periodic table and you go deeper and deeper into some of those elements, this electron configuration can get very long. So what we said you could do is find the nearest noble gas and put that in brackets, and then you would just have to continue the electron configuration after that, whatever comes after that noble gas, up until the point or the element that you're looking to fill out the configuration for. All right, that was a lot of stuff. All right, well, there's another way. This is our second half of the chapter. There's another way to show more visually the arrangement of electrons in an atom, and that's with orbital diagrams. Now, in an orbital diagram, you have, you can either show them as little boxes, as this example has down here at the bottom of the screen, or you can just draw out little lines, little blanks, and fill those in. So those would be representing your subshells or sublevels, orbitals, and then you see there's little arrows on the blanks or inside the boxes. The little arrows represent the electrons. Now, if you remember back to the first half of the chapter, we said that you can only fit 2 electrons per orbital. So you can see there's only 2 arrows in each one of these boxes or on each one of these lines, because each one of the lines represents an orbital. So you're not going to have any more than 2 arrows on a line or a box because you can't fit any more than 2 electrons. All right, so there's 3 rules that apply when we're drawing these orbital diagrams related to electrons. You have Abel's principle. He says electrons occupy orbitals of the lowest energy level first, okay, which we said the lowest energy level is closest to the nucleus. So that means you're going to be filling the electrons into the lower energy levels first. You're not going to start out in like a p orbital or d orbital. You're going to start out in that 1s. Okay, you have Pauli's exclusion principle. We had Pauli during our last unit. He was part of our timeline and in our other notes, and he says that each orbital can contain at the most 2 electrons, and the 2 electron spins. Okay, so let me back up a little bit. So you were looking at these arrows on these orbital diagrams, and you can see that one arrow goes up and the other one goes down. Well, that's representing a different spin. Okay, each electron is spinning in an opposite direction. A little bit more on that in a second. All right, then you have Hund's rule. Okay, this states that single electrons occupy orbitals in a specific sublevel until each orbital contains an electron, and then they'll start to pair up. So according to Mr. Lundquist, the way he likes to explain this is you think Hund He said he uses Greyhound, Hund, if you think about the busing company. So you go to get on a bus and you see that there are people sitting in seats. Normally, you're not going to go sit down next to a person that already is occupying a seat unless you absolutely have to. You're going to take a seat that does not have anybody sitting in it. So he said that's the way he tries to describe Hund's rule. So in other words, when you're filling these arrows in, and we'll do some examples in a minute and you'll be able to understand it a little bit better, you're going to put, for example, you have 3 orbitals here. Okay, you're going to put 1 electron into each orbital first before you start pairing them up. Just like if you were to get on the Greyhound bus, the Greyhound bus, you would not be sitting in a seat next to somebody unless there were no other options for you. Okay, then you had to sit down next to somebody. So just kind of think of it that way. And we'll come back to these rules as we're filling in the orbital diagrams, and they'll make more sense. All right, so here's an orbital diagram example for oxygen. If you remember, we did the oxygen configuration. And so we have our boxes here instead of our lines, same thing, doesn't matter. So the numbers represent your energy levels, 1, 2, and 2. And then the letters represent the shapes, of course, of the orbitals, the S and the P's. Each box represents an orbital within the shell or sublevel. And then, of course, the arrows represent the electrons, okay? And the arrows go up and down, showing a different spin, okay? Electrons must have opposite spins within the same orbital. They just can't get together, go in the same direction. It just doesn't work. If you want more information on that, you can watch this video, but just remember they have to have opposite spins, which are going to show as opposite pointing arrows. Okay, so just wanted to show you some more examples of what they look like. These are orbital diagrams showing correct and incorrect ways to draw out. So if you look at this one right here, this is showing you, okay, so you're going to be filling the 1s orbital first. So we have opposite spins on our electrons, and we move to our next orbital, which is 2s, and again, opposite spins. Then we had 3 electrons left. Well, instead of putting 2 in the first orbital and then 1 in the second, remember we said, based on Hund's rule, you don't want to double up unless you have to. So each one of these last 3 electrons gets their own orbital. Okay, they don't like to share unless they have to. So that's what we meant by that. Okay, and then down here with Pauli's exclusion principle, there was just, I guess it's actually this one right here. It shows that 2 electrons cannot spin in the same direction in the same space. Actually, I don't have that example on there. It doesn't look like. That would be 2 arrows pointing in the same direction, in the same orbital, but I don't see that mistake on here anywhere because all of these are pointing in opposite directions. Okay, this one's also the Hund rule. You can see how they try to pair up 2 electrons here before spreading them out. And they even have an orbital here that doesn't have anything in it. So that would not happen because they would spread out like this, you know, until they absolutely had to pair up. Okay. All right, so remember, there's a certain number of electrons that can fill each level. And we said the s orbital can hold up to 2. So here's your s orbitals here. You can see that there's 2 columns. So that's basically representing your 2 electrons. When we get to the p level here, that there are 6 spots there. So the p orbital can hold up to 6 electrons. And we haven't done much with the d orbital, but if you count, there's a total of 10 running across this middle section of the periodic table, and it can hold a maximum of 10 electrons. All right, so when creating orbital diagrams, it's easier to create your electron configuration first, okay? And then you kind of have your map for how to do your orbital diagram. All right, so step 1, use a periodic table of electron configuration to help you create your electron configuration first for the element, and then use that electron configuration as well as other sources such as charts or tables provided in this PowerPoint to help you create the orbital diagram. Okay, so I'm going to give you a little step-by-step how to do this. And once you get the gist of it, you won't have to be this detailed anymore. But so based on the orbital diagrams, the S's, the P's, the D's, and all the numbers that we use when creating the electron configurations, you'll need to set up boxes or lines. So you can either do the boxes or you can set up the little blanks, whichever you prefer, to represent all the S, P, and D orbitals used in those configurations. Okay, so you'll have the 1s is only got the one orbital, because remember, it only holds 2 electrons. 2s is the same thing. Then when you get to the p orbitals, remember we said that the p orbitals will hold up to 6 electrons. Well, remember, you can fit 2 into each box, so that's 2, 4, 6. So for any of the p orbitals, you're going to have the 3 lines or the 3 boxes, okay? You may not use them all, but you're going to have them. Any of the s orbitals is just going to be 1 box, because we said the s orbitals only hold 2 electrons. And then if you get to the d, if you get that far, with an element that far into the periodic table, you're going to need 5 boxes. 1, 2, 3, 4, 5, or 5 blanks, because we said the d orbitals can hold up to 10 electrons, and remember, you can fit 2 electrons in each orbital, so 5 boxes times 2 is 10. And you may not have to carry it out that far. It just depends on how far you are on the periodic table. So you'll set up your boxes. All right, so figure out your electron configuration. So we're going to use oxygen, okay, since we've been working with that. So first determine that. Okay, then you'll know how many orbital diagram boxes or lines to format in your preparation for creating your orbital diagram. So we're going to need 1 line for the S2, we're going to need 1 line for the S2S2, and we're going to need, this is a p orbital, so remember we said p orbitals get 3 lines or 3 boxes because they can hold up to 6 electrons. So you're going to have, for the p's, you're going to have 3 lines or 3 boxes. Okay, then you're going to start throwing in your arrows, okay? So first look at your 1s. You're going to do these one at a time. Look at your 1s, and it has 2 electrons denoted by our superscript here. So you'll draw your first arrow in, that's 1, and then your second arrow, that's 2. So you're pretty much done with the 1s orbital, and we have opposite spins on our arrows or electrons, so we're happy there. Then we're going to move on to the 2s2 orbital. Okay, so we'll go to the second box. I know my arrows are thicker here, not sure what happened, but anyway. So look and see how many electrons you have. We have 2. So same thing, you're going to have 1 up and 1 down. So we have opposite spins on our electrons, and we filled that orbital, so we're done with the 2s orbital. And lastly, we have to move on to 2p. Now look, 2p has 4 electrons, and we got to remember Hund's rule, okay? Electrons will not pair up in the same orbital until absolutely necessary. So we're going to add 1 electron to each one of those lines in the p subshell. And usually when you do that, you just make them all pointing up. All right, well, we said there was 4. Well, we only have 3 lines, so we need to add 1 more electron to fulfill that 4th one in the p orbital. So now we can go ahead and start adding our second electron, and usually you just start with the first box in the orbital there, and then you make sure it's opposite spin. So now you want to check to make sure you have the right number of electrons. There's 4, 5, 6, 7, 8. And do we have 8 arrows? 1, 2, 3, 4, 5, 6, 7, 8. And they're opposite spins in the orbitals. Yep, and the opposite spin in this orbital. And then these 2 don't have a second electron with them, so they're fine. So that is what your orbital diagram would look like for oxygen. All right, so let's look at this. This is our check for understanding. Which of the following orbital diagrams is incorrect because it violates Hund's rule? Remember Hund, I told you to think of Greyhound buses, and you're not going to sit next to somebody unless you absolutely have to. So if there's seats available, okay, we need to spread those electrons out. So which one of those has paired up electrons that actually had another seat for it to sit in, so to speak? Okay, we filled this orbital, we've got 1. Okay, that's cool. And we filled this orbital, and that's only got 1. That's okay. Let's go over here. We filled the S, 1s, we filled the 2s, and look at our p orbitals here. We still have a blank spot, and we've doubled up. So we really should not have doubled up here until this one was filled in. So your answer for this is letter H. All right, let's look at an orbital diagram for fluorine. You would have done your electron configuration first, which looks like this. Okay, if you want to take a second to try to do your orbital diagram, you can pause the video here. Okay, but the next thing you should do is go ahead and create your diagram format, and we have an 1s orbital, we have a 2s orbital. Let's see, you have a line for each one of those. And remember, we said the p orbitals can hold up to 6 electrons, so you have to draw 3 lines. I put 2p on all of them. You really only need to put it once, but just for teaching purposes, there's going to be 3 orbitals in that 2p. Okay, here is your answer. You're going to start with 1s2. There's 2 arrows, so you're going to put the 2 arrows representing the 2 electrons there in opposite spins to make sure they go in a different direction. Then you move on to the 2s orbital. It also has 2 electrons, so you're going to put 2 arrows in that orbital. It is now filled because you only put 2 electrons per orbital, and again, opposite spins. The way you would do 2p, there are 5 electrons. When you drew it out, you should have drawn 1 arrow going up, 1 arrow going up, 1 arrow going up in each of the orbitals, okay? And then you're going to go back and add the down arrow in this first orbital and then the down arrow in the second orbital. You're going to leave this one alone because it's only 5 electrons. Okay, so then you got 2, 4, and 5. So this last orbital has actually got space for another electron, but it doesn't have it. Okay, so that's your orbital diagram for fluorine. All right, let's look at one for phosphorus. You got to do your electron configuration first, which looks like this. Again, if you'd like to pause the video to try to figure out your orbital diagram, you can pause it here. What you're going to do next is you're going to draw out your blanks. Okay, so this one goes out a little further. So we have a 1s orbital here. We have a 2s orbital. We have a 2p orbital, so you'll have your 3 lines for the p's. Then we move on to a 3s orbital. Remember, there's only 1 orbital for the s's. And then we move into the 3p orbital, so you're going to have 3p. And again, with the p's, you're going to have 3 blanks because it can hold up to 6 electrons. All right, again, if you want to pause it to try to figure out your orbital diagram, please do so. But I'm going to reveal our answer. So this is what the orbital diagram looks like for phosphorus. Okay, so you start with 1s, has 2 electrons. You're going to put the 2 electrons in the 1s orbital, opposite spins. 2s looks the same way. 2p is full because we said the p orbital can hold up to 6 electrons. So you're going to, the way you do it is technically you put the arrow going up in the first one, the arrow going up in the second one, arrow going up in the third one, and now you go back and pair them up. The second one going down with the opposite spin, second orbital in the p, you have the arrow going down, and then the third one as well. So that orbital, the p orbital, is full. Move on to the 3s, 2 electrons. 1 going up, 1 going down, so they have opposite spins. That s orbital is now full. And then let's get to our 3p orbital, which only has 3 electrons. So you're going to spread them out. Remember, based on Hund's rule, they don't pair up unless they have to. So you're going to have 1 electron in each orbital, and then you are done. Okay, so these orbitals are not full, but that's okay, because that's what phosphorus looks like. Potassium. Okay, complete an orbital diagram for potassium. Okay, if you want to do your electron configuration first, so potassium's electron configuration looks like this. And as you can see, the further we get on the periodic table, the longer the electron configuration is. Now, set up your blanks next. Okay, this one's going to be carried out a little further because we're going to move from the 3p orbital into the 4s. And again, the s orbitals have only a spot for 2 electrons, so you only need 1 blank. Okay, if you want to pause it here so you can try to figure it out before I reveal the answer, please do so. The answer for the orbital diagram for potassium looks like this. Again, you will start with the 1s orbital. It has 2 electrons, opposite spins. 2s orbital has full with 2 electrons. Again, 2 electrons, opposite spin. 2p orbital is full because p can hold up to 6, and we have 6 electrons. And again, the proper way to do this would be arrow up, arrow up, arrow up, and then go back and put your arrows down, okay, because they don't pair up until they absolutely have to. Just get in the practice of doing that so you can remember that rule. So now we're full, 2p6, the 2p orbital is full with 6 electrons, and we move on to 3s. It has 2 electrons, so 1 up, 1 down, and now that's full, opposite spins. The 3p orbital, it also has 6 electrons, so you're going to do this one the exact same way you did the 2p, where the 1 up arrow, 1 up arrow, 1 up arrow, okay, and then go back and do the 1 down, 1 down, 1 down. Again, that's just practice so you can remember Hund's rule. And then we look at the 4s orbital. There's only 1 electron in the 4s, so you only need 1 line representing 1 electron. Okay, and that is your orbital diagram for potassium. Okay, so there's some additional videos I've included in here if you're confused or just need different perspectives or different points of view on how to do these orbital diagrams. But the key to this is you've got to understand how to do electron configuration first, and then you need to remember that s orbitals only hold 2 electrons, and p orbitals can hold up to 6, and then d orbitals up to 10, so that you know how many lines or boxes to draw for those different types of orbitals. Okay, I just threw in another electron configuration chart here. So you can see the S's and P's and D's. Another one here, just giving you different versions, whichever one you prefer or like better. Okay, and then there's another version, another orbital diagram resource. That is just a different way of looking at it. I don't particularly like this one, but hey, you know, some people might like it. So, checks for understanding. Which one of the following is the correct electron configuration for a ground state nitrogen atom? Just means stable. All right, so looking at these, you can eliminate some right away because look at this, we doubled up and we still have a spot. So you don't even have to know anything about nitrogen to know this one's wrong. Let's look at this one. Okay, this looks right, but now look, we've got 2 spinning in the same direction. Can't have that either. So we've got to mark that off. This next one, look at this. These are both going in the same direction. Can't have that either. So if you know your rules, you don't even have to know how many electrons nitrogen has to know that D is your correct answer. We have opposite spins here, and we have not doubled up down here because we don't need to. So D is the correct answer. Which electron configuration denotes an atom in its ground state? Again, taking a look at these and just knowing your rules, you can eliminate some. Okay, let's look at this one. We've moved on to a second orbital before filling this first one. So that wouldn't happen. So this is not, you can eliminate that one. Looking at this one, you've got 2 electrons going the same direction, and we can't have that. They have to have opposite spins. They need to look like this one. So B, we can eliminate. Let's look at C here. You've got opposite spins, looks good. Opposite spins look good. We got opposite spins, but hey, wait, we've doubled up before we filled the other 2. So no, that would not happen. Okay, this arrow would be over here in this orbital. All right, let's look at this one. This one can be a little tricky because I told you when you add the arrows, usually you add them in sequence, okay? So we've got opposite spins look good, opposite spins look good, and we haven't filled, you know, doubled up, you know, we're good with this one. But let's just take a look at the last one. And we can almost eliminate immediately because look, we've got electron here, and we haven't filled these orbitals yet to be able to move on to the next. So that's not right. So even though they didn't put the arrow here in this middle box, this one pretty much, you know, satisfies all our rules. So this is the correct answer for this one. What's the electron configuration for an atom of germanium? This is where you're going to need to probably look at the periodic table for this one. And you would find germanium on there. It would be element 32 because these are written in your noble gas configuration. So you would need to back up and take a look and see what the noble gas is that comes right before germanium, which is argon. Okay, so now we can eliminate C and D because that's krypton. Krypton comes after germanium. All right, so we're going to look at, you probably don't even have to know germanium's electron count. If you can just eyeball these, we got 4s2, looks right. Once you get past 4s2, you're going to end up being in the d orbitals, and the first d orbital is D, not 4d. Okay. So this would be your correct answer here. That's just for you knowing that periodic table and knowing the order of the S's and the D's and the P's. Okay, but you could have taken a look at and figured your electron configuration another way. That's how I did it because I knew that 3D comes before 4D. So you're not going to have a 4D here without a 3D in front of it, if that makes sense. So your answer is A. All right, and that is the end of part 2 of the second half of the section 1 notes for unit 3. Okay, if you have any questions, guys, you know where to find me. And I might try to make a second video with some more examples if we needed. So just look out for that.